So in this section, we're going to talk a bit about the connection between diffusion and random walks. And so the basic idea is that on the macroscopic level, we have diffusion. But diffusion is actually the result of a large number of tiny particles and what you see as diffusion is the average behavior of those many small particles. So something like Brownian motion, for example, this is the random motion of particles suspended in a fluid, and it's the motion that's produced by collisions with particles of the fluid. So you can imagine some little speck of dust or pollen being bombarded on all sides by water molecules and kind of knocked a little bit this way and a little bit that way, and it follows some jaggedy random path. So on the microscopic side, we have random walk or random motion, Brownian motion, something like that. And then on the macroscopic side, we have diffusion. So how do we quantify something like this? Well, we say that we need a probability distribution to talk about this. So a probability distribution on the line can be given by some non-negative function that has total integral equal to 1. So that's full probability is 1, right? And the interpretation is that the probability of a random event x taking a value between two numbers a and b, well, that's going to, so that the notation for that is the probability that x takes a value between a and b, like so. This is going to be just the integral from a to b of f. So let's look at a particular example, and this is a particularly important example, the normal distribution. So the normal distribution, or Gaussian curve, or bell curve, has a lot of universal properties, and it tends to show up in many places in probability and statistics. So the normal distribution with mean mu and variance sigma, so these are two parameters, is given by this formula right here. So it's an exponential, it's centered at mu, and then it's flattened by the sigma here and there, which help rescale it. So what does that mean in a particular case? Well, here's 3 examples of the normal distribution. These are all with mean at 65. So maybe I'll just mark that in here somewhere. So where are we? There's the mean for each of these guys. And I've taken them with different variances. So with the first one, we've got a variance of 8. That's a small number, so it's pointy. It's fairly concentrated around mu. As we go out to a variance of 15 and a variance of 30, you see it gets flatter and flatter, but it has the same sort of qualitative shape as the original one, and it just gets more sort of broadly dispersed. So now I've taken 2 intervals of length 20. One interval goes from, and here let me highlight it a little for you. So from 25 to 45 in each of these. That's the bottom of the red zone right there. And then on the other hand, we also have the one that goes from 70 to 90. So each of those intervals have the same length in each situation. But you can see that the probability measure associated to those two is very different. So in the first one here, we have that the probability of getting so I chose this normal distribution centered at 65 with these different variances for supposing this is maybe like the score that you get on some exam in some random class. Probably not my class because my averages tend to be higher than 65, but anyway, so the chances that you get a score between 25 and 45%, well, you have a 0.6% chance of having that. It's a tiny, tiny fraction. Whereas the chances that your score is between 70 and 90, well, you have 26% chance. So a bit over a quarter of the area under the curve is over that interval right there. And then if you, as you increase sigma, you see that the relative measures become sort of closer together. In fact, what's happening is they both are becoming relatively closer to being just a function of the length of the interval. So down here at sigma equals 30, you can see that the chances, so this is when the scores are really spread out. There's a lot of variance, a lot of variation, and maybe a lot of outliers. Then you see here that the probability you get a score between 25 and 45 is now like 16%, which is fairly big, and the chance that it's between 70 and 90% on the exam, well, you've got a 23% chance of something like that. So that's how the normal distribution works for different variances. If I were to change the mean, then that would just shift the curve, just translate it to the left or right, so that it would be centered around a different point. And that's also how the idea of using a probability distribution to assign probabilities to particular events works. So we're going to be looking at the idea of a random walk. So suppose that x of t is the location of a random walker. So the location of a randomly moving particle, say, at time t. So time t is, maybe t seconds after being released from the mean. So we imagine taking some little randomly moving thing, and we place it at 65, and then we let go, and it just randomly wanders around. So what's going to happen? Well, for a short time, it's going to be somewhere very close to 65. So we would expect to have a bell curve that's concentrated very tightly. So it should have a very small variance around 65. For a very large time, well, the little sucker could have wandered off anywhere. So the variance is probably going to be much bigger. So we say that the likelihood of finding our little random particle in some interval at time t should be the integral from a to b of this normal distribution time x integrated, let's see, so this is with 65 and sigma with respect to x, and then that should be for some variance which we think of as a variance which is increasing with time, because you can get spread further and further apart. So then the question becomes, what function of t should we use to be our sigma? And so there's a hint if we look back at some of the things that we've already seen. So if we look at the heat equation, we saw a couple of solutions. And so this isn't for a general D. This is specifically for the case when D is equal to 2. So we saw one solution that was x squared plus 4t. Another solution was e to the minus 18t sine of 3x. And so you can look at those and go, okay, so what's the relationship there between the space and time and the way they scale? And maybe that gives you a hint. Maybe that doesn't give you a hint. We have more hints, though, or more evidence of what we should do. When we saw that the diffusion constant was given in terms of length squared per time units, then that tells you that length squared, or distance squared, behaves like d times time. Or, in other words, that space units squared are proportional to some constant, let's just call it d because it is, times time, right? So putting that together, we conclude that sigma squared over 2 should behave like d times time. Or in other words, sigma should be the square root of 2 dt. So if we make that substitution in the formula that we had before, then we get the following solution of the heat equation: 1 over square root 4 pi dt e to the minus x minus mu squared over 4 dt. Will be a solution of our general heat equation. Okay, so we'll talk more about this one in the next video.